Thank you very much, Professor Zhang, for organizing this workshop, and thank you, Professor Gao and Professor Wang, for having me here, and thank you everybody for attending my talk. So my area is originally natural language processing, and I'm not a biologist originally, but I now work on the intersection of linguistics, computer science, and biology. And today I want to convince you that linguistics and biology are basically two sides of the same coin. And today we have another talk at the end of our program from Professor James Zhou, also about language-guided biology. Our kind of in the same theme, but very different in style in the sense that my NLP is classical NLP and James's NLP is more deep learning NLP. So stay tuned for the last talk as well. Okay, so to start with, I would like to tell you that my background in NLP a little bit, but I just say that my student is actually much more famous than I'm. You probably haven't read any of my papers, but you have definitely, every single person in this room have read Ashish Vaswani et al. Is the most cited paper ever probably in the history. And he is actually my first student. That's a coincidence. But so nowadays people say, oh, how come your student is so much more successful than you? But I think that's the way it should be, right? Your kids are supposed to be better than you. Your students are supposed to be better than you. Otherwise, where's progress, right, in human civilization? So, so how I re-entered computational biology? Well, actually, when I started my PhD, my late advisor, wanted me to work on the intersection of NLP and biology, except that I hated it so much at the time. 20 years ago, I wanted to just do NLP. So I really didn't do very much about biology. I left biology altogether and just to focus on language because I love languages so much. But it's a kind of coincidence that after about 10 years, after I moved to Oregon State, a biochemistry colleague randomly asked me a question in one of the faculty events. He said, do you happen to know something called stochastic context-free grammars, which come from your field, but we use it to model RNA structures? I was like, yeah, exactly. That's what my advisor wanted me to do for my PhD, except I didn't do it, except I just wanted to do NLP. But that was actually after 10 years of NLP research, and I suddenly had a eureka moment on the spot that all these 10 years of like parsing and translation research on natural language can be applied to RNA structures very easily, and the impact will be bigger because the sequences in biology are, RNA sequences are much longer than natural language sentences, right? So in SARS-CoV-2, we have 30,000 nucleotides. That's much longer than any natural language sentence that we can ever have. So, by the time he asked me this question, I said, I want to come back to biology. So I did linear fold and linear partition for RNA folding before COVID. But that was still a side project. Like I was before tenure, so I had only one student working on it. But after tenure, I realized that this is going to be big because COVID was an RNA virus, and mRNA vaccine is also RNA vaccine. So I kind of shifted completely during COVID from NLP person to a biologist. So I worked on linear design, which I'll talk about more, which was published in Nature later for mRNA vaccine design. Okay, so that's the background. And so just before I go into any technical details, I want to convince you that RNAs are basically like English and Chinese, another human language. And it's so nice that RNA structure is so linguistic. It's very recursive. It's very kind of very balanced, well-balanced kind of parenthesis structure that you can just convert it to like parse tree, which is very similar to our natural language parse tree. Hopefully I can show the middle one. Oh, the middle one. Okay, sorry. The middle one. Okay, yeah, thank you. Like this natural language parse tree and our RNA parse tree are exactly the same structure. They're just recursive structures using context-free grammars. So there are a lot of parallels between natural language and biology. Like sentences are sequences and structures are secondary structures or content map in proteins. Oh, by the way, RNA secondary structure is not like protein secondary structure. It contains way more information than protein secondary structure. It's more like protein content map, basically. So it's between secondary and tertiary, basically. So syntactic parsing is basic RNA folding. And for many years, they have been using the same algorithm. They have reinvented the same algorithm in two different fields without knowing each other. So biology is always about 15 or 20 years after NLP. And they got stuck there, for the n-cubic kind of algorithms, where n is the sequence length. That's way too slow. And in natural language, it's very common to do linear time parsing. Like as you hear me speak right now, in your brain, even though you don't realize it, right? Because you just scan from left to right. If you read a newspaper sentence, you scan from left to right, and you don't wait until the end of the sentence. They say parse. You parse it right away, right? You parse it incrementally, And we do that in RNA folding as well, except that it's kind of co-translational folding or co-transcriptional folding. And I just basically extended my work from linear time parsing to RNA folding, and that's or linear fold. That's before COVID. Right, that's the first linear time folding algorithm for RNAs, and it's much, much faster. But when COVID hits, everything changed. And I realized that this kind of linear time folding algorithm will be useful because COVID is so long, right? The genome is 30,000 nucleotides. But I wanted to do something even more direct. I wanted to help the against the virus more directly. So I emailed my friend Rijo Das at Stanford Medical School. I said, how can our work help fight the pandemic? Back in January, because hundreds of people are dying every day in Wuhan that time. Initially, he said he doesn't have any idea, but after a week, he said, I got a great idea. Come to Stanford, we'll talk. So I went to Stanford, and he gave me a 2-hour mini lecture of mRNA vaccine. And at the time, I don't even know anything about how vaccine works. But in those 2 hours, he convinced me that mRNA vaccine is the way to go. Of course, at that time, January of 2020, nobody in the world knew about mRNA vaccine. Very few people knew about that. And I later extended my linear fold work to linear design to design the more stable mRNA vaccines. So just a quick story. So we all know that mRNA vaccines are great. It won a Nobel Prize, but it has one catch. That is, it's very unstable because RNAs are mostly single-stranded, and it's not as stable as DNAs or proteins, and it can easily degrade. Once it degrades, it doesn't translate to the spike proteins that you wanted, and you got less, antibodies induced. So the question is, how do you design more computation? How do you computationally design more stable and efficient mRNA sequences that will stay longer in your cell and will, generate more proteins and more antibodies? So the mathematical problem for mRNA design is actually very easy. It's the inverse problem of translation, but translation is deterministic according to the table. But design is non-deterministic because each amino acid can be expressed by multiple triplet codons due to the redundancy in our genetic code. And because of that, you got a combinatorial explosion problem, right? So if you multiply the number of choices together, you got a humongous number. It's way more than the number of atoms in the universe. So you cannot enumerate them one by one. That would take billions and billions and billions of years. And which one should you choose? Because they are all synonymous. They all translate to the same spike protein that you wanted. So Moderna published a paper, interestingly, right before the pandemic, December 2019, that convincingly showed that you wanted to choose the most stable mRNA in this huge ocean of alternatives, because the more stable, it lasts longer, it produces more proteins. But how to choose, how to find the most stable one? That's a very hard question, right? So in his office in Stanford, my colleague, I said maybe I can solve it, using computational methods. And Rijo Das said, no, forget about it. It's NP hard. You have no hope. So he wanted to use cross-sourcing plus my linear fold to do it. But I said, maybe I can do it. Give me some time. I'll try to solve it. So after a few weeks, I solved it. But after I solved it, I realized I didn't invent anything new. I just, copied a very old, very classical algorithm for NLP and just kind of adapted it to a new problem. Okay, so there are just only two ideas. The first idea is representation. So we borrowed some concept called word lattice from AI, from old classical AI, classical NLP. For example, when we do speech recognition, as you hear me speak, but because I speak too fast or have an accent, you cannot hear very clearly whether I said veal or meal in isolation of context. But of course, given context, you can disambiguate. But anyways, that's the representation of all the possible sentences in the space of the sentences I might have said. And so you do the same thing for the mRNA design problem. So each amino acid can be a little DFA or a lattice, and then often it's just the third nucleotide that you have a choice. But sometimes you have more choices. You have 6 choices for leucine, serine, and arginine, and so on and so forth. You just stitch all these little lattices or DFAs or finite state machines together. You got a very long, thin mRNA design lattice, which encodes the exponentially many alternatives. But that doesn't solve the problem. That's just a change of representation. But that paves the way to how to find the most stable path from the beginning to the end. That is lowest in free energy, because lowest in free energy means the most stable. Okay, so here's the crucial second idea that we also borrow from NLP. That is called lattice parsing. And in lattice parsing, you can give it a language model, but it's kind of a context-free grammar, weighted context-free grammar, and you can kind of efficiently parse all the sentences in this lattice without enumerating them one by one, because enumeration would take exponentially longer. So in very quick time, you can find the most likely sentence and its syntactic structure. So this algorithm is actually from 1961, 60 years before pandemic. And I didn't invent a new algorithm. I just used the same algorithm, but I changed the ingredients. Instead of the English word lattice, I used the mRNA design lattice I just described. And then instead of English grammar, I used the RNA folding grammar, which encodes stability instead of grammaticality. But same algorithm. So in about 11 minutes, we can find the most stable RNA sequence in this vast ocean of alternatives, along with its optimal secondary structure. So that's how this story first started. I'll skip the theory behind it. Is that there's some theory computation. But just to give you just some result, so this is the wild type. Without our design, it's very unstable. You can see there are a lot of single-stranded regions. The red part is single-stranded. That's why it can easily be cut down to pieces. But with about 11 minutes of NLP, you can design a completely different sequence with a completely different secondary structure, so, which is mostly double-stranded. The single-stranded parts are very, very rare. And because of that, you almost turn an RNA into a DNA. And DNA being double-stranded is much harder to break down. And then we did experiments with Stamina Therapeutics, a company in Shanghai. They did experiments for us, and their experiments were quite surprising. They showed more than a 100-fold increase in antibody response compared to the standard codon optimization methods used by, say, Pfizer, Moderna, and CureVac. And when we submitted to Nature, the editor wanted us to at least try one more vaccine because you can just be lucky on COVID. So we tried another vaccine, varicella zoster virus, VZV, also works very well. But one of the reviewers is actually a bit more picky. He said, why don't you compare with the most successful Pfizer-BioNTech vaccine, compare head-to-head to see whether you're better than that sequence? That's kind of a very harsh question because that's already, by the time we submit this, it's already a very successful commercial product, the Pfizer vaccine, and we are just doing a research project. But nevertheless, we compare them head-to-head, and we're still much better, significantly better than BioNTech Pfizer sequencing, both binding and neutralizing sequences, neutralizing antibody response. So here's the two-dimensional optimization. So not just stability is on the x-axis, basically measured by minimum free energy. The lower, the better. The more negative, the better. On the y-axis, that's the second dimension of translation efficiency, which is measured by codon optimality. So it turns out the different codons for each amino acid are not exactly equal, not exactly the same, because human genome prefers, let's say, GC-rich codons and does not like AU-rich codons. So if you use a rare codon, you would kind of wait forever, and you have to wait much longer, so you don't translate as much proteins as you wanted. So you want to prefer frequent codons. So that's called codon optimization, and that's a very local approach. Just basically for each amino acid, you just prefer more frequent codons, and that kind of goes up in the y-axis, but does not go up. It does not improve stability very much at all. It improves only a little bit because GC-rich codons happen to be more stable anyway, but that's just a coincidence. So that's the codon optimization. But everybody else in the industry, like Moderna, Pfizer, BioNTech, CureVac, they're all doing this codon optimization before our work. And then we can do, we can go all the way to the left to find the most stable sequence in this huge space. Which was previously impossible to reach. So Moderna did a lot of random mutations around its sequence. That will take like billions and billions of years to even cross this dashed line. So it won't go very far. So that's linear design. I would skip the experimental results because basically it says it's much more stable, produce much more proteins, and have hugely better antibody results. And this is the head-to-head comparison with the Pfizer-BioNTech sequence. That sequence is actually very similar to our baseline in our two-dimensional grid, but it's a lot better in protein expression than our baseline, but still a lot worse than our sequences. And our sequences are still significantly better in antibody response, both binding and neutralizing antibody. And this is the second virus, the VZV virus I mentioned. It's also a lot better. So I'll skip that. I'll just quickly summarize this part of the talk, the first part. So we have the AI algorithm from classical NLP 60 years ago, and we just converted it to this new problem. And it can design more stable and efficient mRNA sequences without chemical modification, because everybody knows that chemical modification won the Nobel Prize. We have found a completely orthogonal alternative approach. Because it's completely orthogonal, it can be combined with chemical modification. And in fact, a modified version of our design got strong clinical trial results in Laos, was published here. And you can use it for other modalities like circular RNA, self-amplifying RNA, or protein replacement. You don't need to do it for vaccines. You can do it for protein replacement, gene editing. You can do anything. So Sanofi already licensed this technology back in non-exclusively back in 2021. And I started a company called Coderna. The many other companies are under negotiation with my startup. And Regidas, my Stanford friend, also published a paper using our designs in linear communication. That's completely independent of ours. Also confirmed linear design's advantages. So here's a funny kind of side story. So that year, when we published this paper, Katalin Karikó also won a Nobel Prize for mRNA vaccine, the chemical modification. So which is completely orthogonal to our approach. There's a conference. She organized a conference in Berlin, and that year I was there to give an invited talk. But during her keynote, she actually made fun of me. She said, today there was a mathematician who doesn't understand immunology. So that was funny because I'm not a mathematician. But yeah, so are we running out of time?
Still 2 minutes.
2 minutes, okay. So this is my startup, Coderna, and you can try this web server. You can design any sequences for the protein. So I'll skip the bonus track because that's RNA proceedings talk. You can go to the Wednesday talk. And I will just say that to the very last slide, that biology and linguistics are just the two sides of the same coin. We have a lot of other kind of parallels between the two fields, and I've done a lot of in this field. So I would close here, and thank you for your attention. I would like to take questions.
We have time for a quick question. Go to the microphone. Yeah.
Thanks for a very nice talk. I have a question that, so is the RNA stability always has to be achieved at the cost of translation efficiency? Or
yeah, that's a very good question. So yes, here, in a very extreme case, it is like so here is the most stable one. It's actually very low in codon optimality, and this is the highest in codon optimality, but not very good in stability. So this is the kind of a feasibility limit curve. You can increase the importance of the second dimension, but you cannot cross this line. You want to push to the top left as much as possible, but you cannot cross this line. Yes.
Is it related to the double stranding of the RNA?
Sorry.
Is it related to the double stranding?
Yeah, it is related to double stranding. Yeah, the double stranding makes it more stable. Yeah. Thank you.
Okay. Let's thank Liang again for the great talk.